In this section, we will look at the process evaluation as part of process synthesis. Nowadays, with the more climate awareness, it is getting more and more important to consider our activities as chemical engineers in terms of the three dimensions of sustainable development. And you are learning more about this in a sustainable development and industry course unit, okay, where you will discuss these factors in much more detail. When we are synthesizing a chemical process, we think about the process economics, that is the economic viability of the process, as well as its technical feasibility. And this is very commonly known in the market as techno-economic feasibility reports. And normally, once you have a techno-economic feasibility report, that decides that if we are going to go ahead with the detailed design phase or not. Okay, so if your techno-economic feasibility report dictates that the process is not going to be either technically feasible or it is not going to be economically feasible in the next let's say 20 years, so normally we stop our evaluation and the process design there. But if your techno-economic feasibility report say, okay, yes, the process is technically feasible and also it's economically beneficial, then we proceed with the detailed design phase. So technologically and economically, these are the two main factors obviously we consider about our process. But we must also consider the impact of our process on the environment. Okay, and the impact is not only the direct local impact, and not only also just to be compliant with the legislation, but the actual impact in terms of our society as well. Okay, so our process needs to be beneficial in terms of its economics, in terms of the environmental factors, and also its impact on the society as well. So in your design project business case that you will submit towards the end of this semester, you will focus on the sustainability of your proposed process as well. In this unit, we will mainly focus on the flow sheet performance relating to process economics, okay? But I will definitely try to bring point of view of sustainability as well, how it affects our process and our choices. In order to evaluate the proposed process designs, we need information and preferably quantitative information. And these process models can provide much of the information that we need. Obviously, the models need to have some relevance to the reality, and this requires us also to be proficient users of these models. Okay, so please take a few minutes to read the text on the slide. But basically, we need to have good physical property models, as we discussed in lecture 1 live session, and you can get more detail in the book of Robin Smith, Appendix A. For the models to be really useful, they also need to consider issues other than the cost. For example, the toxic nature of your process and how it can affect human life. Also, these models need to be able to account for recycles and in-process sequences. And one of the biggest challenge of these models is that models normally take quite some time to evaluate the process because they are very iterative in nature. So it takes a long time. So some of the commercial softwares that can help us generate these models that we discussed in previous slide are listed here, like Aspen, HYSYS, Pro2, and GPROM. And so this slide first gives us an overview of the strengths of these commercial softwares and then some of the key limitations. Okay, so in terms of its advantages of these softwares, they can be used for a range of applications like hydrocarbons and commodity chemicals. They can consider a range of different phases of chemicals. They have very good physical property database and can account for most of the unit operations. Okay, they can be good for sensitivity studies and simple optimization, and can consider steady state and dynamic simulations, or in some cases unsteady state simulation, but then you need extra packages to consider the unsteady state simulations. In terms of their limitations, so these softwares often require initial good guesses, otherwise it might take them very long to converge in terms of different variables. Also, not all unit operations might be included, so you might have to look for some different packages as well. Some new compounds or biochemical compounds might not be present in the software database, so you have to find ways to include them. And finally, the last 2 points are the last two limitations are actually the limitations of the user more than the limitations of the software itself. Be warned that simulation is not design. Okay, it is just a way to evaluate your design in terms of its technical and economic factors. And the last point is that if you have wrong input of data, if you have used poor properties or wrong properties, then obviously it is going to affect your whole design as well. Okay, so it is very important that you look for reliable and correct physical property databases as well. So this slide reminds you of the definitions of some performance metrics used to evaluate chemical processes. For example, reactor yield that look at the how much the product is produced within this reactor. So that looks at desired product produced in the reactor times the stoichiometric factor that comes from the chemical equation divided by the reactant fed to the reactor. Okay, so that is just for one pass of this reactor. And then we have another definition that is called process yield that looks at the product produced in this whole process. So that looks at the desired product produced that is here at the end of this process times its stoichiometric factor divided by the reactant fed to the process. Okay, so this quantity here. So it does not consider only the reactor but to the whole process, and then we can calculate our process yield. Here we apply those definitions to commune production process using the data given in commune production case study. Okay, and here we define the yield with respect to benzene. You can define the yield based on any of the reactants or products. Okay, so we use the stoichiometric factor of 1 since 1 mole of benzene gives 1 mole of cumene. And you can see these streams and the associated molar flow rates in the case study data that is provided to you on Blackboard. Okay, so if you look at it, you can see that benzene and propene react to form cumene, but this is a competing reaction which reduces the overall yield of cumene because cumene is going to react with propene and going to form an undesired product that is diisopropyl benzene. Okay, and also some of the cumene is also going to be lost when we are going to separate diisopropyl benzene from cumene as well. And here you can see that the reactor yield is 50%, but the process yield is much higher because we have recycling of the reactants in the system that actually enhances the overall process yield. This slide reminds you of some of the other important performance matrices for evaluating process design. It is important to identify which performance indicators are useful and meaningful as you try to find the best flow sheet. And defining what is best is often part of the design process, and normally different targets that you set for your process, like energy targets and area targets and number of equipment or number of shell targets. These targets provide one way of defining what is best process. We may be interested in revenue generation, which relates to product yield for a fixed feed flow rate. We may be interested in capital investment, which depends on the type, size, and operating conditions of each unit. We may be interested in operating cost. The raw material cost may be fixed or variable depending on how the problem is defined and how volatile the market is. Okay, as we discussed, for example, for the case of benzene and cumene production. The cost of energy and other materials are also important in terms of operating cost. Some or all these issues might need to be taken into account when we are talking about the economic performance of our process. It is often convenient not to take into account the costs that are likely to be similar for various options. For example, labor costs and overheads, because different process variations are going to cause you same labor costs and overheads. Okay, so it is not important to include them in your analysis. In this unit, we will focus mainly on annual costs and revenues rather than the economic performance over the whole life of your plant, that is around 20 to 25 years. So we will be focused on mainly on the total annualized. And you can find more detail of these different terms in case studies material that I have provided you in their appendices. In a process flow sheet, there are interactions between various processing units, and mostly the reactor is at the heart of this process, as we talked in terms of our hierarchy of chemical process design. Okay, and the type and the conditions or configuration of this reactor are going to affect the whole process. The conversion and the selectivity of the reactor are going to affect the composition of the effluent that we need to separate. It means that depending on the conditions of the reactor, we have to set what are the conditions of our separation unit and the composition of the feed. Okay, so the reactor not only affect the downstream of the process, but also the upstream as well, because depending on your reactor conditions and your separation unit, you are also going to design your recycle and purge streams. And once you have designed your reactor and separation unit or recycle systems, then we look at the energy requirements, because we want to maximize our energy recovery between different processing units. And once you have recovered the maximum energy possible, then you have to look into external utility systems, and then you have to design the utility systems as well in terms of cooling water or steam systems. So please take a few moments to consider the interactions that are noted on the slide and see how these choices can be affected by the heart of this process, that is the reactor. In the previous slide, we talked about how the interactions between reactor separation and recycle systems can affect your process design choices. This slide emphasizes the point that once you have a fixed structure, the conditions within that flow sheet can be varied to find the best performance, whatever the best design might be. So the complexity of a process design is threefold. First is to find the units and how to connect them in the best possible configuration. Second is to look at the optimization of each unit in terms of its process conditions, flow rates, temperatures, pressure conditions. And finally, see the optimization of the whole process, because the optimization of one individual unit is going to affect the optimized parameters of the next unit or the unit before that. Okay, so you have to look at the optimized whole process. So these are the three factors that we need to consider when we are talking about process synthesis. So here we finalize the material for chapter 0 and chapter 1. And these chapters have outlined the nature of the problem of process synthesis. Okay, the ill-defined nature of the problem and the many alternatives have been highlighted. We also looked at some of the complex relationships between different processing units within a flow sheet, and also talked about the performance issues and the challenges that we normally consider when we look at the process synthesis of a chemical product. This slide re-emphasizes the complex nature of process synthesis, and that it does not have simple solutions. There are not simple methods to address this problem, but one way of addressing the problem is to start with not a very good solution and develop it into something better. And we call this method the evolving design method. A drawback of this approach is that the options can be dismissed or set aside before there is a full understanding of their impact on the flow sheet. And an example of it, for example, if a proposed change reduces the conversion in the reactor, it might be rejected because we obviously don't want to reduce our conversion. But the same change could bring benefits because the material of construction for the reactor now might be much cheaper. So this slide stresses the need for a wide range of options to be considered, and not dismiss before there is enough information to make an informed decision about the advantages and disadvantages of the options being considered. So this slide further discusses the concept of evolving a process design, where we can use the onion logic and heuristics to guide our design and the number of options that merit being evaluated. Okay. At each point, the designer or the design team consider options, alternatives, and evaluate the options. Okay. But there are several drawbacks of this method as well. For example, a choice between alternatives cannot be evaluated well without completing the flow sheet and optimizing it. Okay, so we have too many options and too many solutions to compare without optimizing it. So it takes much longer to evaluate all these options. In chapter 7, we will look briefly at how mathematical optimization can be applied to overcome some of these shortcomings, but it is important to mention that optimization based approach have their own limitations too. Okay, the need to consider several options and to improve operating conditions for a fixed flow sheet lead to iterative process presented in the diagram here. Okay, here the parameters relate to the process variables such as temperature, pressure, and phase, and these are the design degree of freedom that are, as designers, we are allowed to vary. Okay, and here the word structure relates to the choices made about the type of the unit and the connection between them. So when we have a finalized or fixed flow sheet, then as a designer, we can vary the process parameters and the structure of it to some level, and then we can see how it affects the overall performance, as we will be discussing in the next lectures. There is a lot at stake in decisions that need to be made. Obviously, it's a huge investment, and it's a kind of a potential impact in terms of its safety as well. Okay, so don't forget the Bhopal incidents. So decisions need to be based on good information. And who make these decisions? So sometimes it's the project team or the project leader, others in independent reviews within the company, and sometimes it's the external bodies such as the environmental agencies and health and safety executives. Hopefully, chapter 0 and chapter 1 have given you a feel for the nature of the process synthesis and the challenges it presents. Please take a moment to reflect on the main message of these chapters. Okay. So these introductory chapters aim to achieve some of the learning outcomes at fairly basic level. The subsequent chapters will obviously explore these outcomes in further detail at higher cognitive level, including comprehension and analysis and application, and we will look at in the next chapters.